Okay, so this is going to be week 5 ground school. This week we're talking weather theory. So basically the science behind weather. Um, what I always tell students is for weather theory, if you have a fundamental grasp on physical science, you can pretty much think your way through um, any situation or anything involving weather, and you're going to be okay. So, the FAA loves to ask, drives all weather on Earth? And the answer to that question is weather occurs due to the uneven heating of Earth's surface, right? So, different areas of the Earth receive different amounts of sunlight. Those differing amounts of sunlight result in different amounts of temperature, so different heating patterns. When you heat up air, it becomes what? It becomes less dense, right? So then you'll get areas of low pressure, areas of high pressure. Those differences in air pressures are what creates winds. Okay, so now you have the very basic fundamentals of weather patterns. You have different temperatures, different air pressures, and those are creating wind. So the main thing from this slide, the FAA will ask you, why does weather occur? And it occurs due to the uneven heating of Earth's surface. So, like I just said, warm air, as air warms, molecules spread out and become less dense. This results in lower pressure, um, and warm air rises. So, because the warm air is less dense than the cooler air, it rises above that cooler air. Another thing that you need to know is that warm air can also hold more moisture. So the maximum amount of moisture that can be held within uh, a body of air is dependent on its temperature. So the higher it is, the more moisture it can hold. Cold air, so as air cools, molecules compact, right? Just basic fundamental science. Anything cools down, it becomes more dense. So cold air becomes denser and sinks. Cold air holds less moisture. So the colder a body of air, the less moisture that it's going to hold. This picture right here is just demonstrating how we get atmospheric pressure. So if you take 1 square inch of the atmosphere down at sea level, when you measure that all the way up to the very top of the atmosphere, wherever they say it ends, I don't know, 100,000 feet. I think it's like 200,000 feet or something. That's where they say the atmosphere actually ends. But if you take that 1 square inch at sea level, that square inch will weigh 14.7 pounds. Okay. Um, what this picture is showing us is that just 18,000 feet, so just between sea level and 18,000 feet, pretty much half of that weight uh, of that 1 square inch is contained between sea level and 18,000 feet. So the air is much, 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 much denser between sea level and 18,000 feet than from 18,000 feet up to 200,000 feet, right? So it's showing you here at 18,000 feet that 1 square inch of air from 18,000 feet up to the end of the atmosphere is only 7.4 pounds. So the air is much, much denser, closer to the ground. So high pressure. So now we're going to talk about pressure systems, high pressure versus low pressure. So when you hear high pressure, you should think denser air. High pressure systems move clockwise and the air pushes down and out. Okay. So if you see a high pressure system on a map here, this is a surface analysis chart. These little H's right here represent areas of high pressure. So what I mean when I say they rotate clockwise is if you were to see a map of the winds around this high pressure system, you would see them rotating clockwise, like this way, rotating out. Um, the air pushes down and out. So when we're thinking about um, weather systems, high pressure systems generally result in better weather. The reason for this normally is because the air is being pushed down and out. Bad weather is created normally when air is pulled up, when the atmosphere is unstable. So high pressure systems are doing the opposite of that. They're pushing the air down and out. Okay. Sometimes you'll hear high pressure systems called anticyclonic, as opposed to cyclonic, which is low pressure. And then what we call an elongated area of high pressure is a ridge. You don't see ridges very often, but you would see them on this chart. This is where you would see a ridge on a surface analysis chart. Don't worry about this chart too much right now. We'll get into what this chart is, what it means next week. Low pressure. So low pressure system is less dense air. So this air it's an area of lower density air than the air around it. So relative to the air around it, this is a low pressure system. And it just works opposite of the high pressure system. It moves counterclockwise and it pulls the air up and in. Because it pulls air up and in like a tornado does, we call it cyclonic. And low pressure systems mean worse weather. Okay, this should make sense because low pressure is pulling air up and in. When you cause air to rise, that's how you develop clouds, that's how you develop rain, that's how you develop worse weather. So a trough is an elongated area of low pressure. This is much more common. These orange dashes right here on this surface analysis chart are the troughs. That's what a trough looks like. Isobars. So isobars are lines connecting areas of alike pressures. The pattern created by the isobars is called the pressure gradient. The pressure gradient shows how quickly the pressure is changing over an area. So you'll see here, these lines right here, these red lines are isobars. Okay, and these numbers next to them are showing what that isobar is. So 995 is this area in here. All this area contained inside this line is a pressure of 995 millibars. That's what isobars are. You can see here, the isobars are close together right here. What that means is the pressure is changing a lot over a short distance. So you're going to have high winds, right? When the pressure's changing a lot, pressure's changing quickly, uh, you're going to have higher winds. You can see up here the same scenario. Out here, where the pressure is not changing rapidly over short distances, you're not going to have very high winds. Okay, the Coriolis force. So the Coriolis force is created by the rotation of the Earth. It's only apparent over large distances. In the northern hemisphere, it deflects air to the right, causing it to follow a curved path instead of a straight line. The amount of deflection differs depending on the latitude, and the magnitude of the Coriolis force differs with the speed of the moving body. So the faster that the moving body is spinning, the greater the deviation. Think about if you were spinning around on a, let's see, yeah, if you're spinning around on a one of those things they have in a playground where you stand on it and then you spin it. If you were to throw a ball straight or try to throw a ball straight across to someone else on the other side of the merry-go-round, they the ball would not travel in a straight line. The ball will curve to the right or the left based on your direction of motion. This is the same idea. Okay. So what we see here um, is as we have wind patterns uh, on the Earth, because of the Coriolis effect in the northern hemisphere, if the body of air is moving this way in the northern hemisphere, it'll deflect to the right relative to its motion. The same thing happens here. If you have a body of air moving from the north to the south, it is deflected to the right along its relative motion, right? It's always going to the right based upon which way it's heading. In the southern hemisphere, it's the opposite. So the body of air will be deflected to the left based on its relative motion. So the Coriolis force is one reason that we have the wind patterns that we have on Earth. Another reason is the friction force. So the pressure gradient and the Coriolis effect create wind. The pressure gradient forces wind to move from high pressure to low pressure. The Coriolis effect deflects that wind to the right in the northern hemisphere. Okay, so all our high altitude winds are, our winds at 3, 4, 5, 6 up to 40,000 feet, higher than that even, are affected by the pressure gradient and the Coriolis effect. But wind, generally within 2,000 feet of the surface, is greatly impacted by friction with the surface, which results in different wind speeds and directions. This shift usually causes the wind along the surface to blow at an angle across the isobars. So the FAA likes to ask this question, why are the surface winds different than the winds aloft? And the reason is because of friction with the surface. Okay, so you'll see slow near the surface, you'll usually see slower winds and winds that are heading in a different direction than the winds aloft. Global wind patterns. This isn't super important to know. I just put this in here because it's interesting. But how this basically works is as the Earth heats up, this air along the equator becomes less dense, and it rises, and then it's deflected to the right by the Coriolis effect. Around 30 degrees north, you'll see sorry, around 30 degrees north, the flow is eastward, causing the air to converge and create a high pressure. Um, and then closer to the surface, the air flows back towards the low pressure area near the equator, and the Coriolis deflects this air to the west. It creates the trade winds. So what we basically end up having are these cells of air that are continuously moving um, up and down. Basically, they get warmer, they move north, they get colder, they come back. So they rise and then they descend, and they rise and then they descend. And the Coriolis effect, as they come back down, deflects this wind to the left, to the west, because remember, in the northern hemisphere, it'll be deflected to the right relative to its motion. So looking at it as we are, it's deflected to the left. But if you flip around and act like you're on this line, it's being deflected to the right. And this gives us our trade winds, right? What Columbus and they used to sail from Europe to the States was caused by this cyclical nature of our weather pattern. What we have here demonstrated is sea breeze. So this is adiabatic cooling, is what we call this. So adiabatic cooling is when air cools down because its pressure decreases. So what happens on the beach is land and water have different what's called specific heat capacities. Specific heat capacity is the amount of energy it takes to change 1 degree uh, in a surface. So water has a very high specific heat capacity. It takes a lot of energy for water to heat up or to cool down. Land does not, compared to water, has a very low specific heat capacity. So at the beach, during the day, the land heats up very fast. So as the land heats up fast, it heats up the air above it. That air, because it's hot, rises uh, and as it rises, it cools. And the relatively cold air from over the water now moves in to take up that space, or because that low pressure has been created by the rising warm air, and this creates wind that flows from the ocean over the land. So, once again, the process works like this. The sun heats up the land quicker than the water. As the land heats up, it heats up the air above it. The air rises and expands, leaving low pressure here. The cooler air over the water seeks that low pressure to fill that gap to try to equalize and causes wind to blow from the sea to the land. The land breeze is the same scenario, but happening at night. So now at night, um, the water will maintain its heat longer than the land. So the land will now be the cold sink in this scenario. At night, the water will be warm, so it will heat the air and the air will rise. And the cooler air from the cold land will move out to sea and cause wind to blow from land to sea at night. All right, so the term stability. Stability relates to the atmosphere's resistance to vertical motion. A stable atmosphere resists vertical motion. So if you have a stable atmosphere, if air is disturbed upwards, the stable atmosphere will dampen down that disturbance. If you have an unstable atmosphere, it's less resistant to vertical motion. So if you have a disturbance, the disturbance will be magnified and it will continue. Um, Instability generally means turbulence and worse weather. So we want a stable atmosphere. We talked about adiabatic heating and cooling, but this is temperature change due to the expansion or compression of air. So if air expands, the temperature will decrease, and if air compresses, the temperature will increase. Lapse rate. So the lapse rate is the rate at which temperature decreases with an increase in altitude. We use the lapse rate to help determine the stability of the atmosphere. The average lapse rate is 2 degrees Celsius per 1,000 feet. So that's what you're going to use when you're trying to determine the stability of the atmosphere. You'll look at the winds aloft, and for every 1,000 feet, the temperature should decrease by 2 degrees. If it is not, we will say that the atmosphere is unstable. The dry adiabatic lapse rate is 3 degrees per 1,000 feet, and the moist adiabatic lapse rate is between 1.1 and 2.8 degrees Celsius. The difference is moist air cools slower than dry air, so we just use the average lapse rate, which is 2 degrees. Temperature inversion. So a temperature inversion occurs when the temperature increases as altitude increases. So, that's the opposite of what should happen. Temperature should decrease as altitude increases, but you could have a temperature inversion, which happens when a layer of warm air slides over a mass of cool air. It's going to create poor visibility, smooth air, fog, haze, and low clouds. So it's going to be smooth flying, but it's going to be poor visibility. You'll commonly see this on a cool, clear, calm night. So what happens on a cool, clear, calm night is when you don't have clouds at night, clouds normally act as kind of insulation, is the way to think about it. They trap heat between where the clouds are and the ground. So when you don't have those clouds, the ground will radiate its heat away very quickly. And that will quickly cool the air near the ground relative to the air above it. So now you'll have very cool air near the ground and slightly warmer air above it, and that'll be a temperature inversion. Humidity relates to the amount of water being held in the air. Warm air can hold more water than cold air. And then we have two terms here. Well, we have an important term here, relative humidity. Oh, sorry, my dog's barking. Relative humidity is the actual amount of moisture in the air compared to what could be held in the air at that temperature. The example of this is 100% humidity air at -4 degrees in Alaska has about 20% of the water content of 68-degree day in Florida at 100% humidity. This is because very, very cold air does not hold very much water compared to warm air. So you'll see that reiterated in the bottom bullet point. Amount of moisture in the air depends on air temperature. So the warmer the air, the more water it can hold, the more water vapor it can hold. Dew point. Okay, so the dew point is the temperature at which the air reaches a state where it can hold no more water. The FAA likes to ask this question and likes the answer to be the second bullet point, the temperature at which the air will become fully saturated. So when warm, moist air rises, it begins to condense and form clouds at the altitude where the temperature and the dew point are equal. So we have two formulas where you can approximate what the base of the clouds is based upon the temperature and the dew point. What you'll do is you'll take the temperature and subtract the dew point, and then if those numbers are in Celsius, you'll divide them by 2.5, and then you'll multiply by 1,000. That'll give you the approximate cloud base height. If your temperature is in Fahrenheit, your dew point's in Fahrenheit, you'll divide that number by 4.4. So clouds are um, basically just condensed water. Clouds can be made of water droplets or ice crystals, and the droplets condense on small pieces of solid matter in the air called condensation nuclei. So those things are dust, salt, or combustible materials or combusted materials. Clouds near the surface are just fog. So fog is basically just a cloud along the surface. So I'm not going to narrate these slides because I don't have anything else to say about these ones. So I'll just go through them. You can pause and copy down what they say. All right, that is it for this lesson.